Thank you everyone for joining us today for permanganate treatment of oil field produced water. I'm the moderator today, Ashley Swingle with Carus. Our speakers are John Sanders and Lyndon Berwick, also with Carus. You can go to that next slide, perfect. A few housekeeping items before we get started. We are recording this webinar and everyone is kept in listen-only mode. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with the question and your contact information to follow up directly after the webinar. If you're interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. And next. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. And we can't forget to mention our social media platforms. We encourage you to connect with our Carus page, as well as our team members on LinkedIn, where we're often sharing upcoming events, including webinars, industry articles or news, sharing relevant posts from industry experts, and more. Next. At this time, I would like to take the opportunity to introduce our speakers for today, John Sanders and Lyndon Berwick. John is the Regional Sales Manager of the Gulf region for Carus. He graduated from Trinity University in San Antonio, Texas, with a Bachelor of Science degree in both biology and chemistry. John resides in Houston, Texas, and is a member of American Water Works Association, American Chemistry Council, and the American Society of Sugarcane Technologists. Lyndon Berwick is a technical and field specialist for Carus. He has over 15 years of chemistry experience in both research and industrial sectors, including oil and gas production, environmental geochemistry, potable water treatment, and oil field specialty chemical sales, applications, and service. After completing his PhD in 2009, he worked as a full-time research fellow with the Organic and Isotope Geochemistry Center at Curtin University in Western Australia. Lyndon has been with Carus for over 3 years since moving to the United States from Australia in 2018. He currently resides in Savannah, Georgia. And at this time, I will hand it over to John.
Thank you, Ashley. Thank you all for joining us. We're going to initially start off presenting some information that's relatively new and still emerging on the use of permanganate in industrial water treatment, and in this case, specifically on the treatment of produced water. As we know, recycling and reuse of produced water is critical in reducing the cost of treatment and environmental impact these days associated with oil and gas production. As the chemical parameters and key performance indicators, KPIs, for produced water quality continue to tighten, operators and service providers are seeking new and innovative treatment strategies to try to meet their performance goals. So the outline, we're going to initially discuss some oxidation produced water treatment, briefly review some properties and reactions of permanganate, get into some common key performance indicators, and then Lyndon is going to go in more detail through some produced water treatment goals and look at some specific testing data from the field that we've done related to iron removal, oxidation reduction potential, as well as water clarification. And then we're going to specifically look at some comparisons of permanganate and hydrogen peroxide field and laboratory testing data that we conducted in the Permian Basin. This is your typical produced water treatment flow chart, and what we wanted to highlight here is the area we're generally going to play in this process, and we looked at with our permanganate products are in the advanced treatment, which is pretty typical where the other oxidants are applied as well that work on increasing ORP, precipitate out metals, remove the sulfides before coagulant addition, solid separation, polymer addition and water clarification downstream. So just wanted to kind of highlight this to focus on the sector that we're concentrating on, where we're doing our testament and field treatment. This table is just going to review some common oxidizers that are used out in produced water treatment. Different oxidizers come in different forms. Each of them have their own individual plus and minuses. Chemical oxidizers in general are applied to oxidize the iron and other metals, the dissolved sulfides, and the hydrogen sulfide, or H2S. They also function to help increase ORP, which is very key as the water moves to the treatment and gets stored in either finished water tanks or pits to be going back to the frac. ORP is very important to be maintained. And finally, assist with solids removal and water clarification. I'm not going to review every one of these line by line, but the ones we listed, obviously potassium permanganate, which is the product we focused on. Then you have chlorine dioxide, hydrogen peroxide, which is very prevalent as an oxidizer being used out in the produced water treatment, as well as ozone. And these columns highlight, pros and cons, ranging from everything with how fast the reactions they do, cost of treatment, safety factors in utilizing the products, and things of that nature. And the data from that we've got was referenced from the Produced Water Treatment Fundamentals that was presented back in the Produced Water Society meeting a couple of years ago. Just to focus on permanganate products, permanganate is a highly oxidized form of manganese. So in chemistry terms, permanganate can be categorized into two descriptive buckets, so to speak. Manganese is a transition metal, which is very similar to iron. It's present in the Earth's crust, and it is an essential micronutrient for life. Permanganate, as I said, is a highly oxidized form of manganese. The two products that we typically focus on is our Carus potassium permanganate, which is a solid 97% or greater assay. And then Carusol liquid permanganate, which is our sodium permanganate products. They come in two concentrations, 20% or 40% as pre-dissolved water solutions. And basically they work the same. One of them is a dry that gets made down that we've looked at that, as well as a liquid that's already made down into a liquid product. So we've tested with both products in these. We just wanted to familiarize you with both of these permanganate products. Now the reactivity, to go in a couple of them. There's numerous reactions the permanganate does, and what this chart does shows the reactivity with some inorganic compounds. Sulfides, sodium bisulfite, very, very fast, a second or less for the reaction. Fast reactions, anywhere 15 to 30 seconds. You've got nitrite 3, you've got iron, and you've got arsenic, and it shows the reaction properties. We don't need to go in heavy detail on that, but that's shown to the left. And then lastly, we have our kind of medium fast, 5 minutes or less. That takes us into our sulfide, our manganese. So sulfide, one of the key, the H2S, the dissolved sulfides, which is present in a lot of this produced water that we look at. Permanganate is very effective in its speed of reaction with that. And then iron, as we see in the fast, 20 seconds or less, obviously one of the key metal components that needs to be removed in the finished water before it goes back to the frac. They want, as much iron as possible removed from it. So very important reaction. It's a very quick reaction with permanganate. Lastly, look at some treatment goals and KPIs. And again, they can be all over the place. This was one, again, that we've got during a presentation with Produced Water Society, but some locations are tighter than these, some are looser. It seems to be going a little geared more toward the tighter spectrum, but total iron, usually less than 2 milligrams per liter. I know years ago you could see it just less than 10 milligrams per liter, very easy. We've been out to some recently that are requiring less than 1. So almost all of the total iron needs to be removed. So that's definitely tightened up. Oxidation reduction potential, the ORP, generally they want it somewhere 300 or above. Seems to be common. Some may go 250, but on average, they're very comfortable with 300 or more. The turbidity of the finished water, again, some are very loose, 100 or less, which is not that difficult to meet, but then some want it less than 10, almost closer to drinking water turbidity. And that can, in some cases, be a much harder KPI to meet. Sulfides and H2S are generally 0. They don't want any of that. pH somewhere neutral, 6 to 8. And then finally on the microbio, they want to get as much of it out as possible, usually less than 100. Are these typical? And again, these are just kind of typical on average that we've seen. Some are more difficult, some are more lenient. It just depends what area and what company you're trying to accomplish this for. All right, I'm going to pass it over to Lyndon. He's going to go into more detail on some actual field data, lab testing data that we've gotten. Again, several Permian water sources that we've worked with, both out in field testing as well as testing back in our lab in Illinois. And I'm going to pass it over to him and let him outline some of the studies that we've been doing over the past year or two. Lyndon?
Thanks, John. And just making sure, Ashley, John, that my screen's showing correctly.
Yep, that looks good.
Good, great. So, yeah, as John touched on, some of the KPIs here, the two that are sort of highlighted in red are the ones I want to focus on first. So this will be looking at some field and laboratory data for iron oxidation and the ORP response from a few produced water sites in Texas, in the Permian Basin in particular. So, as I'm sure most people are aware, the oxidation of soluble ferrous iron, the iron 2, to the insoluble ferric iron 3 precipitates is one of the really key treatment goals in produced water. Ideally, the soluble or dissolved iron content should be as low as possible so that you're avoiding potential issues with iron precipitation downstream and during re-injection. So the graphs here show removal of soluble iron with permanganate during field jar testing at 4 different produced water facilities. Nothing really new here except to highlight that each site is slightly different in terms of the initial iron concentrations and also the oxidant demand required. But in all cases, we can see that the reaction occurs very rapidly and can achieve very low residual iron levels depending on the permanganate dose and the starting iron concentrations. So on this slide, the data here is comparing soluble iron removal on the left axis with ORP response on the right axis. Again, with permanganate dose response at 2 different treatment sites, this time site 1 and 4. ORP, as most people will be aware, is a very valuable parameter that is easily measured with online or laboratory probes. Generally speaking, treated water with an ORP above 300 or 350 millivolts is considered to be relatively free of bacteria and should have oxidized the majority of the dissolved iron present into those insoluble precipitates. Those precipitates can then be removed by clarification or filtration. So in both cases here, we see a really good correlation between the 2 parameters. We get that rapid increase in ORP as the soluble iron content is reduced, and particularly reduced below those sort of targets of 1 to 2 milligrams per litre. This isn't always the case for all water types, and I'll discuss a little bit more about that in the next slide. So the graphs here show, again, ORP dose response at 2 different sites and a direct comparison of permanganate with hydrogen peroxide, arguably the most common oxidizer used in the field. We can see similar performance between the 2 oxidants at site 1 on the left there, but at site 2, the permanganate is able to achieve a much higher ORP at the same dose rate as peroxide, so the permanganate being in blue here. For site 2, we actually repeated the test after sampling again several months later, so these were separate sampling events, and we saw the same trend, that really elevated ORP with permanganate compared to peroxide. So one of the questions is, why do we see this different response? A couple of factors involved, I'm sure. Site 1 contains higher levels of both soluble and insoluble iron compared to site 2. I've got those values down the bottom here. But clearly the demand required to achieve a suitable ORP is not just attributed to soluble iron content and soluble iron oxidation. There may also be an influence of organic content and composition, and the actual nature of the organics present in the 2 different waters here from the 2 different sites, and how that those materials may be affecting the oxidant demand and the doses required. So the next set of treatment goals that we want to focus on are for solids removal, turbidity reduction, and overall water clarification. So in this slide, I wanted to highlight the permanganate half of the oxidation reaction. The colors that we've got here, the purple and the brown, are deliberate. When the permanganate ion is dissolved in water, the solution has that distinctive pink to purple color, as John highlighted previously. And then the precipitated byproduct of the oxidation reaction is a reduced form of manganese called manganese dioxide or manganese oxides. And this is has that typical brown to black in color. So MnO2, manganese dioxide, is actually quite a useful flocculant material that can play an important role in water and wastewater treatment. It can act as a coagulant aid or seed material that interacts with inorganic coagulants and polymers. It can help absorb other charged impurities such as charged ions and some organics. And it also provides an active surface area for the oxidation of sulfides by dissolved oxygen. So some of our early site testing illustrated how permanganate treatment in conjunction with the site's polymer of choice combined to result in really high clarity water. The photos here show permanganate treated produced water and what that coagulation with manganese dioxide can look like in field jar testing. So in the middle picture, we see the initial flock formation with MnO2 solids, and then in the last picture, really excellent clarity and solid settling after addition of the typical oil-filled polymer or flocculant. And again, this was achieved without needing to add an additional inorganic coagulant. And again, another quick example, another case study here that shows permanganate treatment of really high solids loaded flowback water. And again, without needing to use a coagulant, we get excellent clarification and solid settling using permanganate oxidation with a polymer alone. So following some of these were quite early observations that we saw in the field. We wanted to look more closely at the advantage of manganese dioxide as a sort of an in situ coagulation aid and verify some of the findings, the visual findings that we saw in the field with some laboratory data. So there's 2 key components to these particular studies, which are tied to the KPIs of total ion removal, and water clarification. So the data here shows produced water treated with 10 parts of permanganate and then followed with an anionic polymer at 3 different dose levels. Again, we see that excellent results were achieved well below the target KPIs for both turbidity and iron, again, without the need for adding another inorganic coagulant. The polymer dose also at 2.5 parts was also about 8 times lower than the dose that was being used at this particular site, where peroxide was employed as the main oxidant. And we see also that increasing the polymer dose to 5 and 15 parts per million also didn't really improve the results here. So our next focus was to look at a direct comparison between hydrogen peroxide and permanganate for these two parameters again, total ion removal and water clarification. The data here from site, this is from site 1, shows total ion removal with and without coagulant addition. The coagulant in this case was polyaluminum chloride. For this particular site, we observed pretty generally similar performance for permanganate and peroxide using the 3 treatment chemical strategy. So oxidant plus coagulant plus polymer. So that's the second and the fourth data columns. But if we compare the 2 oxidants using polymer only, so the first and the third data columns there, we can see a much greater total ion removal with permanganate, and again, without needing the coagulant addition. Another thing to point out here also is that the polymer dose that we used with permanganate was half that was required for the peroxide. So same data here, but for site 2, the same data essentially shows much better improved performance for permanganate against peroxide, both with and without coagulant addition, and especially using just the 2-product strategy with polymer only, which is the highlighted data here in the blue. Peroxide actually failed to reduce the total ion levels to below the target KPI of 1 milligram per litre in both cases, mainly due to insufficient solid settling. Permanganate performed significantly better with ion levels reduced well below the target KPI without using any coagulant. So again, why are we seeing this sort of difference between the 2 sites? The biggest difference between the sites 1 and 2 is in the distribution of iron between the soluble and insoluble phases, and so therefore the total solids content. Site 1 has higher overall total iron and a larger amount of already precipitated solids, and so we see fairly similar total iron solids removal using either one of the oxidizers. On the other hand, site 2 has a much lower total iron content. Therefore, we see poorer settling performance using peroxide because we're not getting that manganese dioxide flock that is provided with the permanganate treatment. The next 2 slides show essentially the same comparison of permanganate and peroxide at the same 2 treatment sites, but this time we're looking at turbidity as a measurement of water clarity. For site 1, there's a similar trend to what we saw for total ion removal. Slightly better performance using permanganate with either the 2-product or 3-product treatment combination, but overall fairly similar results. You can see here, and again this is related to the overall solids content and iron content, we can see that the turbidity of the untreated raw water in the grey data column, that turbidity is very high in the untreated water, so that will actually help natural flocculation and solid settling. But again, the polymer dose required with permanganate was still half that required for the peroxide. Moving back to the second site, site 2, same data this time for clarification and turbidity. In this case, though, we see really vastly improved performance with permanganate in the blue data columns there. Peroxide actually couldn't achieve the target turbidity below 10 NTU, while permanganate yielded the target really easily using either the 2 or 3 product combinations, so polymer only or polymer plus coagulant. So for raw waters like this one at site 2 that had that relatively low iron content, there may be insufficient solids present after peroxide treatment to allow that efficient coagulation and flocculation and solids separation and removal. And again, the manganese dioxide floc produced as part of the permanganate reaction is really advantageous, and it eliminates the need for those inorganic coagulants. So just to finish up, a quick summary of hopefully some of the important takeaways from the presentation. Permanganate, well known as a strong, stable oxidizing agent, used extensively in water and wastewater treatment. It is added to produce water as a first chemical treatment step ahead of clarification or filtration, and reacts very rapidly to remove soluble iron, increase ORP, and improve water clarity. And the results from our field and lab studies have shown that permanganate offers a rapid and effective alternative to peroxide for the removal of a variety of those contaminants and getting that elevated ORP level. Provides an excellent in situ coagulation aid for solids removal and water clarification. It can help eliminate the need to add any inorganic coagulant, and also reduce the required doses of polymer or flocculant products, effectively allowing that simplified 2-product program of oxidant and polymer instead of a 3-product program. It can provide more consistent treatment efficiency and performance for variable raw water types. So if your incoming raw water composition fluctuates quite a lot, you sort of have more of a buffer zone with the permanganate treatment, and can provide a more cost-effective total treatment strategy, either alone or in combination with peroxide, which can also potentially be used as a polisher after permanganate treatment. Thanks everyone for your attention. Ashley, I turn it back over to you, I guess.
Yes, thank you, Lyndon. Thank you, John, for your presentations today. Great information. And thank you everyone for joining. If anyone does have additional questions, feel free to reach out to Lyndon or John. Their contact information is on the screen now, and they will get back to you. So thank you again, everyone, for joining, and have a great day.